Okay, real quick. So moving on to the spin connection in complex dimensional spaces, I want to quickly just talk about how the space is conformal, how it could be conformal, and so that we can understand where the extra element coming from. Okay, so we're going to define a length squared. Now, we're working in a complex dimensional space here, so I'm writing it out in traditional tensor format. Okay, so this illustrates the connection between sort of a while version of the space, which is conformal, in this complex dimensional space. So you see that later when we apply it to the Clifford algebra. Okay, so this is just strictly standard tensor notation. We start with a definition of length throughout the space. Psi here just means some kind of vector within that space, complex dimensional. We can see here that our metric is going to be Hermitian, so Kähler is what they refer to it as. And we know that already from our generators that we discussed last time that that's going to be the case. So I'm interested in taking the differential of that L squared, that's dl L star, L dl star. It's important this is a difference because L squared is really L star, not just L squared. We have complex conjugates in our space, so it makes it slightly different. You can then write it out in parts. And I goofed. Thank you, comment section. We can write out the individual parts. We're creating an affine connection here as defined in this space. I know this is a little weird because what we're saying is, oh, it's a complex dimensional space, but our derivative is relative to our space-time coordinates. How does that work? Well, that's because in reality, this isn't just a standalone space. This is actually a fiber applied to every point in space, and so we're looking at the geometry as it relates to that whole setup. Okay, it's a little bit different. The derivative of our length is proportional to our interval. This is, you can read about Wiles' conformal geometry, and you'll see that that's the case. Plugging all of that madness in back into our equation, and we finally end up with a equation relating this, which would normally be considered the covariant derivative of the metric, and that equals this. You can see that this ends up being, you know, if it were regular space-time, you would have 2b alpha here if alpha were a real only vector, but in this case it's actually got complex values in it, so this combines into that. And that's why when you break this up with tetrads, you get related directly to this, so that the fact that it's complex actually doesn't matter. Okay, you can't just replace this with 2 times a real valued vector and call it a day, because if you remember, or this is no longer the Minkowski metric, but rather the metric of our flat version of our space, whatever that signature may be, and we'll get into what that is in our case. So what we're doing here actually is pretty generic. You could apply it to any number of dimensions if you wanted to. You could apply it to a 16-dimensional complex space and still relate it to the 4 dimensions here again, because it's not a standalone space, but you get this, and you can see that that involves this going on. So if you take the covariant derivative of this bad boy, it breaks up. Try to be good with my handwriting. It's not always easy being easy. It's not easy being sleazy in the way like a straight dog. Anyhow, so if I say that this is actually equal to alpha EMA here, well, this is the complex conjugate, so you're going to get this. And it's pretty easy to see how that will then combine into this. Okay, so that's where that comes from. So this is our equation for the tetrad itself. Right? This is our new metricity condition for our tetrad in this complex dimensional space that allows for links to vary, that is conformal in its nature. And so we have this, our space is defined by our tetrad as well as this additional complex valued vector. So then we go over here, and like we did last time, we're now replacing the gammas with Q. Q is our generator. So just like last time, I literally left the equations up and just did some hand wiping and replacing with different variable names, but you get the idea here. And I'll put this in quotes because it's actually this here. This is this. And much like before, we now have a new W. So instead of omega, I'm calling it W, related to our tetrads in our complex space of a certain number of dimensions. I'm using a Latin index now instead of a Greek one because we're in a complex space. I'm still using capital letters to represent the flat version of that. So this allows me to create now a version of this that works in our complex space as a spin connection. Okay? There's one more thing to do, and that is solve for this thing. Because we're interested in what are some of the properties. Now, you can do a derivation here and show something. If you remember the last time I created this version of it, glossed over a bunch of calculations regarding the gammas and that antisymmetric version. Well, you end up getting something similar. So we're going to say W alpha is defined as 1 over 8, that's familiar, W alpha JK QJ QK dagger minus QK dagger QJ. Then QM D alpha M. So minus or plus. There was now this gamma that we have over here, and it might be plus QM minus QM W alpha, and that is equal to 0, right? No, wrong. Let's do this. Okay. Now you notice what happens with this bad boy is that W alpha dagger, or flip, is equivalent to flipping the J and the K here. This is the case because remember it was antisymmetric before, but now we have to throw in the complex conjugate. I'm going through these properties without deriving them, but I can certainly go through and show you how all that works. In the same way that in spacetime you would derive that the equivalent version of this is antisymmetric in its upper indices. You do that by applying a metricity condition on it relative to the Minkowski metric. Similarly, you would do something here relative to our version of the equivalent of the Minkowski metric, which is Hermitian, and so this becomes anti-Hermitian. Or if you put an I in front of it, it would be Hermitian in that sense. There you go. This W here, defined by this, is our interaction terms. What I want to illustrate here too is this. I don't know if you remember me saying this in the first lecture, is that our rotations, because this is a rotation, our rotations have to be such that Q and Q daggers don't rotate into one another, because then we wouldn't be analytic. We would through purely a rotation, be switching between Z and Z star. And that's fine if Z, if the complex nature of it is fake, which is often done in Clifford algebras, where you insert complex numbers into it simply by reducing. Like if you go from 5 dimensions down to 4, your pseudo-scalar element in your 5-dimensional theory, it really is just I. And so you've injected I into a theory that is strictly a real geometric structure. And then by reducing it by 1 dimension, you get to something that is less dimensions, but each element is now complex in its value. Right? And that can work from any odd number of dimensions if you have the right setup for your Clifford algebra, which you have a similar signature to space-time algebra. One of the degrees is opposite of the rest. You can always do that. So I can take a 5th-dimensional Clifford algebra that's real and reduce it down to a 4-dimensional one where all the elements have complex numbers in it. That isn't the same, though, as being analytic, and I want to stress that. Because in a 5-dimensional theory, you can introduce rotations between those dimensions that you would not see if you were doing an analytic version of a complex dimensional space. It's different. It's very different. And that's something that often people don't do. The people in the Clifford algebra, they just love to keep it real. And so as a result, they introduce rotations, which again, rotations create interactions through symmetries, and introduce rotations that aren't actually, that produce bosons in our model that aren't real, that we don't find in nature. This restriction that you see here, which are derived, I didn't even use rotations to derive it. I just strictly derived it based on a definition of, in this complex dimensional space of a spin connection. This type of rotation, where it involves Q and its dagger, maintains that. So it keeps Q's with Q's and daggers with daggers. That's very important, as you see. Later, when we get into the details next of laying out all of the different states within the models, you'll find that there's exactly 32 specific unknowns. That is exactly what you need for one generation of particles in our 4-dimensional theory. And find again, like I mentioned earlier, that our projection back down from this fiber back into the space-time is what produces all the limitations on the rotations that give us exactly the standard model. Electroweak as well as the strong force, and it's actually quite simple to see. And all of those rotations now are coming from curvature that we've introduced into our space. So we have our complex dimensional space, we give it a metric, we give it tetra, then we produce the tetrad so that we can get the spin connection. Those spin connections give us our interactions. If it's on the left, it's going to produce the electroweak force. If it's on the right, it's going to produce the strong force. Both are actually driven off the same thing. They're limited because we want our system to actually be in a complex space, not a real space that's been reduced down. That requires then our rotations maintain that through it being analytic. We introduce an additional neutral current. The labeling here is not an accident. That comes from our conformal system. We're allowing this thing to scale. And if you think about why that would be, well, it's quantum fields. So it should be conformal because after all, we always are normalizing everything. We're scaling the entire system globally so that we can get probabilistic results. Yeah, so that's that, and we'll get into the next step next.